Right, so let's begin this lecture on gametogenesis. Now, gametogenesis, by definition, is a process of formation and development of the gametes. What we call the gametes are the sperm and the ova. The process of gametogenesis takes place within the gonads. When we talk of the gonads, we are referring to the testes in males and the ovary in female. So don't call things like uterus and penis gonads. The testis is the male gonad, the ovary is the female gonad. The process of forming sperms, which takes place in the testis, is what we call spermatogenesis. The process of forming the ovum, which takes place in the ovary, is known as oogenesis. Okay, I was to give you a question there, but the question has not loaded well, so I'll skip it. Maybe I'll give it to you later. Let's look at the phases of gametogenesis. Gametogenesis occurs in 4 phases. The first phase of gametogenesis is concerned with the origin of the stem cells that will later become the sperms and the ovum. So the origin of the stem cells that give rise to the gametes. During this phase, the key event is this one. Those cells that will later become the sperms and the ovum, they don't necessarily exist within the gonads of the baby initially. They don't exist there, but they're usually from some regions outside the gonads. But then what they do is that they migrate and invade the developing testis, the developing ovary. This happens before birth. So in simple terms, what I mean is when you were conceived in your mother's womb, at some point it started to develop. Now, if you are male, it means that there's a time your testis was developing when you're still in your mother's womb. It was during that time that your testis was developing in your mother's womb that the sperms you have right now invaded the developing testis, and then they stayed there. If you are female, the same scenario. Those cells which are now called oocytes migrated from some regions, I'm going to tell you where, and then invaded your developing ovary way before you were born. Then now they're inside the ovary, they're inside the testis. After those cells have come from wherever they come from and invaded the developing gonads, the next agenda is to make these cells increase in number significantly. Now, let's assume that those cells were about 1,000, which invaded the developing testis or the ovary. And for the sake of discussion, let's use the testis. So let's assume that there were about 1,000 cells that invaded the developing testis. I'm not saying there are 1,000, but let's assume there are 1,000 so that the point I want to make becomes clearer. We know that men produce sperms in millions, yet at this time, there were just 1,000 cells. So the objective here is to increase significantly the number of these potential sperms. So definitely, these cells must increase in number. And the definite way of increasing number is if these cells divide. So my question to you is, if you have 1,000 cells and you want millions from these 1,000 cells, you will subject these cells to cell division. Would you subject them to mitosis, and why? Or would you subject them to meiosis, and why? Which type of cell division will these cells undergo? That is the question. So you can unmute your mic and attempt. Anyone?
Meiosis.
Meiosis.
All right, so David.
Yeah, mitosis because.
Faith, carry on. You're saying mitosis because? Okay, someone said mitosis. Whoever said mitosis, give us a
Mitosis because we want.
I must have lost you, Kwanzo. Okay, who wants to try? Why mitosis or why meiosis?
Let me try and say meiosis. Since meiosis gives rise to 4 daughter cells, and for our case, we need to produce more of the cells to attain the, let's say, 1 million now.
Okay, I get your point. Good. Another person? Anyone with a different opinion?
Can I try, sir?
Yes, Anthony.
It is meiosis because it involves 4 division, and therefore there is production of 4 daughter cells.
Okay, I get your point. So the understanding here is that at least we'll get the 1 million faster.
Sir, can I try?
Yes, you can.
It is meiosis because division of the sperms and ova, it only occurs in meiosis. Mitosis is the somatic cells only.
Okay, I get you. Thank you. All right, so usually it's actually tempting to say that the sperms will divide in a meiotic way, but that's not true. They actually divide mitotically. Now, who can try give me a reason why, if I want to increase in number, I'd rather make the sperms to divide mitotically instead of meiosis, bearing in mind that eventually we need these sperms to divide in a meiotic way anyway, as the speakers who have spoken have actually agreed, except at this step, we need mitosis, not meiosis. You can try. This is based on the assignment I gave you people about cell cycle and cell division. So if you did that assignment, you'd be able to get it right. Yes?
In mitosis,
Mm-hmm.
there is cell replication.
Okay. So, okay, maybe for the sake of time, let me just give you the answer. Now, the answer is this. If a cell undergoes meiosis, usually it will enter into the G0 phase of the cell cycle. But if a cell undergoes mitosis, it will enter the G1 phase of the cell cycle. Or it may enter the G1 phase of the cell cycle. So, if you're starting with 1,000 cells, if you subject these cells to meiosis, those 1,000, it means the maximum you can achieve out of the sperms, out of those 1,000, is only 4,000. because meiosis is an end stage of cell division. However, if these cells divide in a mitotic way, they will enter the G1 phase. And I can see one of you is asking, what is G0, what is G1? It means you didn't do the assignment on cell cycle and cell division. But is there someone who wants to try answer? Help that person know what is G0, what is G1? Okay, nobody, so you will check on what is G0, G1. That was your assignment, eh? And I gave it a while back. So anyway, sperms need to be in millions. If they divide in a meiotic way, you'll only have one division. And so you have a maximum of 4,000 if you're starting 1,000. But if they divide in a mitotic way, it means that the daughter cells can divide again. That is what simply G1 means, that they still have a potential of cell division. So this 1,000 will divide into 2,000, yes. 2 will divide to 4, 4 will divide to 8, 16, 32, and the like. We have multiple series of mitotic division. Because you have multiple series of mitotic division, and all of them are dividing, we have an exponential numerical increase in the number of gametes. That is why they have to do mitosis, not meiosis. So please, you people, check on what is G1, what is G0. You'll also check on what is S phase, what is G2 phase. That was your assignment a while back. After the sperms have increased in number significantly, or the oocytes have increased in number significantly, the third phase of gametogenesis is what we call now the haploid phase. Now, haploid phase is that period where now you want the gametes to have their chromosomal content. So it's a period of reduction of the chromosomal content by half. And the process of doing this is to take them through meiotic cell division. My question to you is, so why should we have these gametes having half of the number of chromosomes? What is the importance of making them have half the number of chromosomes? Anyone?
Trial.
Yes.
The chromosomes have to be half in number so that during fertilization, when the sperm is fusing with the ova, the chromosomal number will now be full, because now this one is half, then the other one is half.
That's very true, and that's the answer. Thank you. After the third phase, the last phase of gametogenesis is what we call the differentiation phase. During the differentiation phase, the gametes mature, both morphologically as well as functionally. So there's some events that take place so that they change anatomically as well as physiologically. Good, so these are the phases of gametogenesis. It is interesting to note that it is only this phase, the first one, where the events that lead to forming sperms and events that lead to forming the ovum are similar. Only this phase is similar. standard, common to both. How the sperms go through step 2, 3, and 4 are different from how the ova will go through these 3 steps. So therefore, that brings me then to now the objectives of the lecture. You know, that was introduction. So this is the objective of the lecture. We want to state where those precursor stem cells that form the gametes come from. We also want to state how sperms and ova go through step number 2, step number 3, and step number 4. Now that we've said it's different. So remember, this is step number 1. But about 2, 3, and 4, we'll check for sperm and ova. Then I'll give you some time to discuss the differences between the 2 steps. And finally, we'll then highlight on the clinical aspects related to the process of gametogenesis. So straight ahead, let's start with the step 1 of gametogenesis, which is the origin of the gamete stem cells. The stem cells for the gametes differentiate from some pluripotent embryonic cells. Pluripotent to mean that they have the potential of becoming multiple things, multiple cell lines. Plural potency. Embryonic cells mean that they're cells of the embryo. Remember, I told you these things happen before you're born, actually way back before you're even a fetus. So when you are an embryo. So those embryonic cells, there's some pluripotent embryonic cells. Those pluripotent embryonic cells are called the primordial germ cells. These primordial germ cells arise from sites which are outside the testes and outside the ovary. Where are these sites? There are 2. We have what we call the yolk sac, and we have what we call the allantois. So yolk sac and allantois are those extragonadocytes, those sites which are outside the testes or the ovary. Yolk sac and allantois are present in the embryo. The cells in the wall of the yolk sac and the cells in the wall of the allantois are the ones that give rise to the primordial germ cells. These primordial germ cells, okay. These primordial germ cells invade the developing gonad. If the developing gonad is a testis, they invade the gonad. If the developing gonad is the ovary, they still invade the gonad. So they're primordial germ cells. They come from regions outside the gonads. They migrate and invade the developing gonad. Now, see this. So let's say, okay, this is what we are called the yolk sac. This developing embryo. You'll understand this much later, this image, but there's something called the yolk sac. These are the cells on the wall of the yolk sac. The same cells are here, the primordial germ cells. They migrate from the yolk sac into the developing gonad. This is the developing gonad. This gonad can either be testis or ovary, but they invade the developing gonad. Once they have invaded the developing gonad, they stay there. They're the ones, okay, you still see here, developing, or rather primordial germ cells migrating into the developing gonad. Once they have invaded the developing gonad, they stay there, but they're the ones that will then constitute the stem cells for forming sperms or stem cells for forming ova. The stem cells for forming sperms are known as spermatogonia. The stem cells for forming the oocytes are known as oogonia. What makes them become spermatogonia and not oogonia is dependent on the gonad that forms. If this gonad that is forming is the testis, then those stem cells will be called spermatogonia. If these stem cells are invading a developing ovary, then those stem cells will become the oogonia. So this is how step 1 is experienced. Okay, someone is saying my voice is low. Let me try that. Okay, sorry about that. Right, so I've said that the primordial germ cells come from what we call the yolk sac and allantois. These cells invade the developing gonad prenatally. So they migrate from yolk sac and allantois and invade the developing gonad prenatally. If this gonad is the testis, then those primordial germ cells become spermatogonia. If this gonad is the ovary, then those primordial germ cells become the oogonia. Spermatogonia and oogonia are the stem cells for the gametes in their respective gonads. We are done with step 1 of gametogenesis. This is common to both male and female systems. Now, I told you step 2, 3, and 4 is different for these two systems, and so therefore, we will talk about them independently. Let's begin with spermatogenesis. Before we do that, I will give you a question. So there's a question that is going to pop on your screen. I want you to answer it. You have 1 minute for it. Right, let's proceed. I think 5 people haven't answered, but I think they're not in class. Okay, now 4 people have not answered, but I'll proceed. Okay, I am projecting what you people have said. I hope you can see it. I can see majority of you have said 2 seconds. In as much as you are wrong, I know why you said 2 seconds. I know what you are thinking. We are going to see. Very few people got this correctly. Okay, so stay tuned for you to know the answer. Now, spermatogenesis takes place within the testis. But where exactly in the testis? It takes place within the seminiferous tubules of the testis. These are the seminiferous tubules of the testis. We did epithelium, and we talked about classifying epithelium. Seminiferous tubules of the testis in cross-section looks like this. We classify this as complex stratified epithelium. So sperms are formed within this complex stratified epithelium. The process of forming sperms starts at puberty. It means that once those primordial germ cells have invaded the developing gonads, the spermatogonia remains dormant within the testis until puberty. That is when now the process of forming sperms can begin. That is when step 2, where mitosis is the primary thing, can now begin. It takes about 64 to 74 days to form a single sperm. Now, this is because of the process involved in forming that single sperm. Now, don't start doing those funny mathematics of primary and high school, of if it takes 2 months to form a single sperm, then how long will it take to form millions of sperms? Then you realize you'll not be alive to see it. It's like asking you, so how long does it take you? How long does it take Daystar University to train a nurse? And the answer could be 4 years. So it takes 4 years to train a single nurse. How long then does it take to train 100 of you? Well, I believe your answer is still 4 years. It's the same thing here. The sperms are produced in bulk. The process of spermatogenesis, only the grave separates us from spermatogenesis. You'll see the difference in female. So spermatogenesis continues throughout life. The best temperature for spermatogenesis is some 2 to 3 degrees below the normal body temperature. It explains why the testes hang outside in quotes, so that the testicular temperature can be lower. The optimal temperature for spermatogenesis is 2 to 3 degrees below the body temperature. So if you're a lady, you have a boyfriend, you can advise them to keep it cool. During spermatogenesis, there are some supporting cells within the seminiferous tubules. The supporting cells of spermatogenesis are known as the Sertoli cells. They're the ones that provide both structural as well as nutritional support to the developing sperms. Now let's go through those 4 steps, those 4 phases of gametogenesis with now spermatogenesis in mind. In step 1, we say that we have what we call primordial germ cells, and that these primordial germ cells migrate to the developing gonad. If that developing gonad is the testis, then these primordial germ cells will be called spermatogonia. Spermatogonia are therefore the stem cells of forming sperms. Spermatogonia are present in the testis. They're the stem cells for forming sperms. They stay in the testis until puberty. When puberty reaches, then we need to do step 2 of gametogenesis with reference to spermatogonia. And that step 2 was now where we are having numerical increase. And we agree that this one can only be achieved by mitotic division, not meiotic division, and we gave a reason why. This process, as I've told you, starts at puberty. So it means that before puberty, the testis just contain spermatogonia. But at puberty, now mitosis begins. Several series of mitotic divisions will lead to formation of what we call the primary spermatocytes. There are multiple series of cell division. There are multiple series of mitotic cell division. It will lead to formation of primary spermatocytes. Because this process of mitotic division leads to formation of primary spermatocytes, we sometimes refer to this process as spermatocytogenesis. So spermatocytogenesis is the process of formation of primary spermatocytes. How does it occur? It occurs through a series of mitotic cell divisions of the spermatogonia, multiple series of mitotic cell divisions. Great. Now we have primary spermatocytes. The primary spermatocytes are present in millions. They're present in millions within the testis. Perhaps from this image, you can also appreciate that even though mitosis occurs so that you eventually form primary spermatocytes, the cells that divide can still retain their potential of being stem cells. So you can still recycle the pool of stem cells. You never lose them. They're always there. Now we have primary spermatocytes. We have gone through step 2 of gametogenesis. Now let's look at step 3 of gametogenesis. This is the step that gives us haploid cells. As we already know, for you to form haploid cells, you'll just subject the cells to meiosis. So meiosis will give us haploid cells. How do we do this? There'll be 2 phases of meiosis. The first meiotic division, also called meiosis 1, will give you some intermediate cells which we prefer calling secondary spermatocytes. So secondary spermatocytes have undergone the first meiotic division, but they have not undergone the second meiotic division. Then the second meiotic division occurs, leading to then formation of what we call spermatids. So spermatids are now haploid cells. If you compare that with primary spermatocytes, which are diploid cells. You realize that because a single primary spermatocyte undergoes meiosis, the common concept is that then meiosis leads to formation of 4 daughter cells. So a single primary spermatocyte gives rise to 4 daughter cells. The daughter cells in this case are known as spermatids. Right. Now, the sperms you and I have in mind look like this. However, the spermatids look like this. It means that there's still some panel beating that the sperms must undergo so that we can have morphological change in the shape or appearance of these cells. The process of morphological maturation was now phase 4 of gametogenesis. So these cells will undergo phase 4. Now, the first thing that happened is that they change their morphology from here to the one that looks like that. This period of morphological change of the sperm is known as spermiogenesis. In spermiogenesis, the spermatids undergo morphological changes, and this leads to formation of what we call spermatozoa. This is the spermatozoa. This is the spermatid. During spermiogenesis, we have a lot of things occurring in the cytoplasm. There's a lot of differentiation that takes place in the cytoplasm, including shedding off of the excess cytoplasm. This process is facilitated by the Sertoli cells, those supporting cells of spermatogenesis. So it's a time that now the cytoplasm of the spermatids change a lot. That's why we call it cytodifferentiation. Now, spermatozoa are the mature sperm cells. Interestingly, when spermatozoa are formed, look at how they appear. At the spermatid time, they're still anchored together. So like the spermatids that came from one primary spermatocyte are just anchored together like that. When you form the spermatozoa, yes, spermiogenesis has taken place, but these cells are still attached to the wall of the seminiferous tubules, as you can see here. Now, definitely, if they still hold to the seminiferous tubules the way some boys hold to their mothers, there's no way they'll get the oocyte. So these sperms must then be freed. The process of freeing the sperms is known as spermiation. It is the process of releasing sperms from the wall of the seminiferous tubules into the lumen of the seminiferous tubules. It's called spermiation. It is not called ejaculation. You and I know what ejaculation is all about. It is more interesting than spermiation. So spermiation is the release of sperms from the wall of the seminiferous tubule into the lumen of the seminiferous tubule so that the sperms are free. In a single day, a man produces about 300 million sperms in a single day. It's a continuous process. You can just conclude and say, what a waste. Okay, I want to give you another question. Check out on your okay, there's a question. I'm using these questions to take attendance, so don't worry.
Yes.
All right. I'll end it there. Two people haven't answered, but I'm hoping I'll get them later. So those are your responses. You'll know the answer shortly. Now, the free spermatozoa are now found within the lumen of the seminiferous tubules. What happens to them? These spermatozoa are then transported along the seminiferous tubule. They'll pass through this region of the testis, which we call the rete testis, and enter into this region, which we call the epididymis. So in simple terms, the sperms move from the testis to the epididymis. Now, what happens to the sperm when they are in the epididymis? First, they'll be stored. Sperms are stored for about 2 to 3 months in the male reproductive tract. It tells you why, if a man undergoes vasectomy today for the sake of contraception, you don't tell them tomorrow you're good to go. There are some sperms within the epididymis and vas deferens which are still viable, which have not been cut off by that vasectomy. And so usually if a man undergoes vasectomy, you tell them you still have the potential until some 3 months later. Then now we are sure the sperms in the vas deferens are no longer viable. During the storage of sperms, okay, whoever that is. During the storage of sperms, an important process takes place. This is called decapacitation. Decapacitation is the process of covering the sperm with some glycoprotein. This green thing here represents that glycoprotein. It is a process of covering sperms with some glycoprotein. We prefer calling them the decapacitation factors. This is the sperm that has been produced from the testis. This is the sperm that is now within the epididymis. It's being covered by decapacitation factors. The importance of decapacitation is to kind of restrain the sperms, because it's like blindfolding the sperms so that they may not be able to identify where the oocyte is. Now, the point is this: the oocyte is not in the male reproductive tract. When the sperms are in the male reproductive tract and their identity molecules are exposed, they are very stupid. They will start looking for that oocyte in the male system. Definitely, it will never be found there. And what will be the end result? They'll be dancing up and forth, running right up and center. They'll be so tired, but they'll never find the oocyte. They'll be so tired that they might die faster, or that they will lose their energy. By the time they're now deposited in the right place, they cannot swim to the site of the oocyte. So decapacitation is just a mechanism of immobilizing the sperm, so to speak. They can still swim, but not very vigorously, but they can still swim. It's just a mechanism of telling them to leer. All right, after storage and decapacitation, I've already told you that they can be stored for about 2 to 3 months and they remain viable in the male reproductive tract. This is different from viability within the female reproductive tract. So one day, hopefully, these sperms can then be ejaculated, and hopefully they find themselves in the female reproductive tract, not in the esophagus or in the rectum. If they find themselves in the female reproductive tract, then the last step of spermatogenesis will take place. What is that last step of spermatogenesis? First of all, let me tell you about the numbers. So a single ejaculate usually has a volume of about 2 to 6 ml. A single ejaculate has a volume of about 2 to 6 ml. Let's take an average, maybe 3 to 4. Each ml of the ejaculate contains about 50 to 100 million sperms. So if you do your mathematics right, then you'll realize that a single ejaculate has about maybe 300 to 500 millions of sperms in a single ejaculate. So ukipata mwenye amekaa dry spell for long, maybe 6 ml. Ukipata yule mwenye Julia alikuwa anaongea about him, maybe less than 1 ml. But the point is this, that each ml contains about 50 to 100 million sperms, and the ejaculate is about 2 to maybe 6 ml. So a single ejaculate holds about usually 300 to 500 million sperms. Unfortunately, out of all those, only 1% of the sperms can climb up. The 99% of the others remain in the vagina. And if you actually wake up as a lady immediately after sex, kwisha wewe, because again, most of them will go down, of course, due to gravity. Maybe it will not even be 1% going up. So you get the moral of the story. All right, so this 1% that goes actually up the uterus and fallopian tube, what happens to them? As they travel through the uterus and fallopian tube, these sperms undergo the last step of spermatogenesis. And the last step of spermatogenesis is what we're calling capacitation. Now, what is capacitation? Capacitation is now the reverse of decapacitation. It is the removal of the glycoprotein covering from the head of the sperm. And what is the purpose of this removal? The purpose of this removal is so that sperms can now be more motile. Remember, they were immobilized when they were in the male reproductive tract. So the sperms then become more motile if they undergo capacitation, where we have removal of the glycoprotein covering. The other reason why capacitation is important, Okay, maybe I've defined capacitation as the removal of the glycoprotein covering, but what's the purpose of that removal? One, the sperms become more motile. That means they can swim faster. They have their energy now back, they can swim faster, they're very happy. But the other reason is that, remember, we had like blindfolded them in quotes. So when you remove this glycoprotein covering, it means that the sperm is able to identify the site of the oocyte, at least from a molecular point of view. They're able to see where the oocyte is because their identity molecules have been exposed. And so capacitated sperms swim faster. So this shows you the sperm that has been formed from the testis. When it enters the epididymis and mixes with the seminal fluid, it is covered by the decapacitation factors. When this sperm then finds its way in the female reproductive tract, then it is capacitated. The decapacitation factors are removed. This sperm can now identify the oocyte because the identity molecules have been exposed. Capacitated sperms swim faster and also are able to identify the oocytes. Therefore, capacitation makes the sperms ready for fertilization. All right. These are the parts of a mature sperm. What we call A is the head of the sperm. Within the head, we have a nucleus and the acrosome. These things form, the acrosome forms during spermiogenesis. B is a neck, and this X here is called the midpiece. The midpiece of the sperm contain several mitochondria. They are within here, several mitochondria. Then we have this one being the principal piece of the tail, and this being the end piece of the tail. The tail of the sperm is largely to give it propulsion motion when it's swimming. Great. So we are done with spermatogenesis. I can see it is 4:25. I'll give you 10 minutes break. So we can break now. We come back at 4:35. Then we talk about oogenesis. I think we'll only talk about spermatogenesis and oogenesis. We'll not be able to talk about fertilization today. We'll talk about it another time. All right, so take your break. 10 minutes. We come back at 4:35. Now we talk about oogenesis. Oogenesis takes place in the ovarian cortex. If you look at this outer region of the ovary is what we call the ovarian cortex. This central zone of the ovary is what we call the ovarian medulla. The ovarian medulla contains blood vessels and connective tissue. The ovarian cortex is where the oocyte develops. These large things you're seeing here represent developing oocytes surrounded by a lot of supporting cells. We call them ovarian follicles. So the ovarian follicles are within the ovarian cortex. That's the site of oogenesis. The process of forming the oocytes begin way before a girl child is born. The process of multiplication of the cells to give you oocytes begin before birth. This is unlike spermatogenesis, where the process begins at puberty. Having said that, it means it takes very long to form a single ovum, in the understanding that even though the process began before birth, some eggs will be ovulated when the girl is 50 years, okay, maybe 45 years. Some eggs will be ovulated when she's 15 years, maybe. And so we can just say it takes several years to form a single ovum. Beyond menopause, women are unable to form the oocyte anymore. So the process of forming the oocyte ends at menopause. The process of forming the oocyte is a cyclic process. It is not anytime, anywhere, any day, anyhow, like the sperm. For the oocyte, there's some maringo kidogo. It is cyclic. Every month, a few or one is the one that is formed. The others wait. No wonder ladies know to wait. The supporting cells for oogenesis are known as follicular cells. These are the cells that surround the oocyte. We call them follicular cells. So let's go through the steps in oogenesis the way we done for spermatogenesis. We are saying that we have primordial germ cells. Way before birth, these primordial germ cells migrated into the developing gonad. If this developing gonad was the ovary, then these primordial germ cells become the stem cells of forming the oocytes. These stem cells are known as oogonia. That is step one or phase one of gametogenesis, the origin of the primordial, or rather the origin of the gamete stem cells. This is similar to what you've seen in spermatogenesis. Now, let's go to step two or phase two of gametogenesis. Remember, phase two of gametogenesis is a multiplication phase. Now, what is unique about oogenesis is that the multiplication phase occurs prenatally, unlike in spermatogenesis, where the multiplication phase occurs after puberty. In oogenesis, this multiplication occurs prenatally, before birth. And usually, we're talking about even around the 3rd to the 5th month fetal life. So what happens? Just like in spermatogenesis, the multiplication phase is a mitotic cell division. Several series of mitosis leads to formation of the primary oocytes. Remember, in spermatogenesis, we would have called them primary spermatocytes. In oogenesis, we are calling them primary oocytes. The primary oocytes, because they have undergone mitosis, these primary oocytes are still diploid cells. Just like the Oogonia, they are all diploid cells. A maximum of 7 million only can be formed. So after everything has happened, in this 3rd to 5th month of fetal life, the maximum number of primary oocytes that can be achieved is 7 million. That means in most cases less, because this is maximum. You see the way Oogenesis is very conservative, very cautious. Now, this is what happens to the primary oocytes. This is prenatal. The primary oocytes become surrounded by the supporting cells. We have called those supporting cells the follicular cells. So slowly, you have a layer of supporting cells that surround the primary oocyte. In addition to the follicular cells that surround the primary oocyte, there's also another thing that covers the primary oocyte. That thing is a glycoprotein covering, just like the sperm was also covered by some glycoprotein. It may not necessarily be the same glycoprotein, but yes, this is still a glycoprotein covering. This glycoprotein covering is known as the zona pellucida. So the zona pellucida surround the primary oocyte. Then external to that, we have the follicular cells. So at this point, we can say that the primary oocyte is surrounded by zona pellucida and follicular cells. I've told you that this happens maybe in the middle of the pregnancy. Towards birth, even more follicles will die. These cells die, and so the follicles degenerate. We reached a maximum of 7 million. What I'm now saying is that by the time we are approaching birth, by the time this girl child is approaching birth, a number of these primary oocytes will have died. They undergo what we call follicular atresia. So you get atretic follicles, follicles that have died. Follicular atresia occurs so that by the time the girl child is being born, poor girl, they are less than 1 million. Now let's see what happens to the primary oocytes even before birth, apart from some of them dying. So we want to focus on these ones which are alive. What happens to them before they get here? Okay, maybe before that we define something. So this complex between, or rather the complex constituted by the oocyte, the surrounding follicular cells, and the zona pellucida. This complex is what we are calling the follicle, ovarian follicle. Now, the primary oocytes are there in the ovary of this fetus. This fetus is not yet born. What happens to the primary oocytes? Remember, primary oocytes are the results of what happened after mitosis. It means that they are diploid cells. So the gametes then need to establish haploidy by undergoing meiosis. So the primary oocytes begin meiosis. And just like in spermatogenesis, meiosis will have two phases, meiosis 1 and meiosis 2. However, how the oocyte undergoes meiosis is very different from how the sperm undergoes meiosis. Remember those steps of mitosis: prophase, metaphase, anaphase, telophase. We borrow similar terms for meiosis, except now you specify. If you are in the first meiotic division, then you talk of prophase 1, metaphase 1, anaphase 1, telophase 2. If you are in the second meiotic division, then you talk of prophase 2, metaphase 2, anaphase 2, and telophase 2. Having said that, the primary oocytes begin the first meiotic division. So they go through prophase 1. The intention is to then move to metaphase 1, telophase 1, sorry, anaphase 1, then telophase 1. But that does not happen. The moment or when the primary oocytes are within prophase 1, they become arrested there. We call that the first meiotic arrest. The first meiotic arrest occurs at prophase 1. We are calling it first because there'll be a second one. What I want you to note is this arrest occurs prenatally. This girl child is not yet born. Prophase 1 arrest takes very long. It takes years. What the implication? The implication is that when this baby will be born, this oocyte will be at prophase 1 because prophase 1 arrest takes years. What facilitates this arrest? The arrest is made possible by the follicular cells. The follicular cells are the ones that secrete a factor known as oocyte maturation inhibitor. The oocyte maturation inhibitor inhibits the maturation of the oocyte. That chemical is secreted by the follicular cells. Those follicular cells that surround the oocyte are the ones that inhibit it. It's the same way your friends are the ones that can sometimes betray you. All right. So the follicular cells actually betray the oocyte. They inhibit it. It becomes arrested at prophase 1. Therefore, this girl will definitely be born when the oocytes are at prophase 1. Remember, they are primary oocytes at prophase 1. She will be born. She will grow until puberty. Those eggs are still at prophase 1. Very interesting. Between the time she's born and the time that she begins puberty, even more cells, or rather even more follicles, will undergo atresia. So that by the time this girl child is reaching puberty, we have less than 500,000. By the time she's reaching puberty, there are less than 500,000 follicles. That may sound little, but it's not actually little. It's just being economical. The reason is, after all, she'll not give birth to 500,000 children. So it's not a big deal. Right. So we have follicular atresia. The follicles die, but we still have those that are alive. The ones which are alive are now less than 500,000. When this girl reaches puberty, she will begin the menstrual cycles. When she begins the menstrual cycles, something interesting happens. Every month, about 15 to 20 of these follicles are stimulated to continue in their development. Part of this stimulation involves completion of the first meiotic division, which means that the oocytes which were arrested at prophase 1, that arrest is undone, and so the oocyte can proceed to metaphase 1, anaphase 1, and telophase 1. The oocyte can complete the first meiotic division. The point to note here is this, that about 15 to 20 are recruited in each menstrual cycle. So this is September, 15 to 20 have been recruited or were recruited depending where they are right now. Then the following month, if you don't conceive this month, the following month may be another 15 to 20. So about 15 to 20 are recruited each month to complete their first meiotic division. You can be doing your arithmetics from your 500,000. By the time this girl is 40 years, how many will be remaining? You will realize there will be still a lot remaining. Because it means if you're recruiting about 15 to 20 every month, that means in a year you'll have recruited less than 1,000, definitely. Less than 300, definitely. You are saying at the time of puberty, you have about 500,000. So there's still enough, even if you are to live for 100 years and ovulate those years, there'll still be enough. So not a big deal. All right, so if the oocyte begins, or rather completes the first meiotic division, that cell that has completed the first meiotic division is no longer called primary oocyte. We call it secondary oocyte. Now, something unique about this division, meiotic division, is that when one cell undergoes meiosis in oogenesis, the cytoplasm does not separate equally. One cell goes with a large cytoplasm, and that is the one we call the secondary oocyte. The other cell becomes very tiny, very little cytoplasm, if any, so it only contains the excess genetic material. We call that a polar body. Meiotic division in oogenesis is unequal, so that you have, if this is the primary oocyte, it will undergo the first meiotic division. The cell division is not equal. That means there'll be one big cell, secondary oocyte, and another tiny one, the first polar body. This is different from what happens in spermatogenesis. The primary spermatocyte divides, undergo the first meiotic division to give you two secondary spermatocytes equal in size. Secondary spermatocytes also undergo the second meiotic division. You give rise to 4 spermatids. All of them are equal in size, which is equal to saying all of them are viable. From one primary spermatocyte, we get 4 viable spermatids. That's different from oogenesis. In oogenesis, the cytoplasmic division is unequal. It's not equal. So the result is this one big cell and a small one. The small one is called polar body. The other one is called, okay, is the line of interest. Now, the secondary oocyte will also later undergo the second meiotic division, and I'm going to say what makes that happen. And that's when you'll form the second polar body. So we've not yet talked about this. We are at this point. I put this image to illustrate to you that meiotic division in oogenesis is unequal. So the big cell is our interest, is the oocyte, but the small one is called polar body. First polar body is gotten from first meiotic division. Second polar body is obtained at the second meiotic division. The first polar body may or may not divide again. So this one, commonly we just end it there. Usually it does not divide, but it may divide. So now we have a secondary oocyte. It has completed the first meiotic division. It needs to undergo meiosis 2 so that it can complete the second meiotic division. So the secondary oocyte immediately begins the second meiotic division. When it begins the second meiotic division, it means that it will go through prophase 2. After it has gone through prophase 2, it will go to metaphase 2. While at metaphase 2, the second magic happens. It undergoes the second meiotic arrest. So the second meiotic arrest occurs at metaphase 2. The second meiotic arrest occurs at metaphase 2. In terms of timing, this one takes place around the time of ovulation. To be specific, 3 hours before ovulation. Remember, the first meiotic arrest occurs at prophase 1, and this was before birth, and it involved the primary oocytes. The second meiotic arrest occurs at metaphase 2. It involves the secondary oocyte, and this process occurs around the time of ovulation, 3 hours before ovulation to be specific. It therefore means that when a woman is ovulating, the oocyte that is being ovulated is actually a secondary oocyte. It's something that has not yet completed the second meiotic division. It's something that has not yet completed second meiotic division. It is still not mature. Now, this might surprise you, but the secondary oocyte, most of the time, does not complete the second meiotic division. It ends there. That becomes the end stage for it. Now, why do I say so? The prerequisite for the secondary oocyte to complete the second meiotic division is if a sperm enters that secondary oocyte. I didn't say if a sperm enters a vagina. I said if a sperm enters the secondary oocyte, if fertilization occurs. That is the prerequisite for completion of the second meiotic division. It is only completed if this egg becomes fertilized. If it is not fertilized, it will never complete the second meiotic division. If it is fertilized, it will complete the second meiotic division. And what will be the result of that? It will mean that now we have one big cell, call it mature ovum for lack of a better term. And then we'll have a second polar body. The purpose of the polar body is to get rid of the excess genetic material. Great. I'd shown you this, told you that these are ovarian follicles. This complex formed by the oocytes, follicular cells, and zona pellucida. We call it the follicle. So by the time ovulation is approaching, the follicle that will be present will be this one, not this type. Because as the follicle matures, the number of follicular cells also increase. And as we approach ovulation, there's a cavity that appears within the follicle. This is in preparation for ovulation. And so this mature follicle is the one ready for ovulation. This one is not ready for ovulation. It is still growing. A mature follicle looks like this. This is a follicle ready for ovulation. The egg here is secondary oocyte at metaphase 2. It's been arrested. So similar thing you're seeing here, this is how the mature follicle would look like. Now follow with me here. This is mature follicle. When ovulation occurs, this is the part that is ovulated. That's the part that's ovulated. The others remain in the ovary. It's not ovulated. We are going to see what that becomes shortly. So let's name the parts of the mature follicle. The other name given to the mature follicle is Graafian follicle. The part labeled 1, we have called it the secondary oocyte. Remember, it's been arrested at metaphase 2. The structure labeled 2 is called the zona pellucida. It's a glycoprotein covering of the oocyte. When we talk about fertilization next week, we will see the purpose of the zona pellucida. The one labeled 3, 4, and 5 represent different populations of follicular cells. We have follicular cells existing in 3 different populations. The population of follicular cells immediately outside the zona pellucida. This population of follicular cells is known as the corona radiata. This one's population of follicular cells outside or surrounding the zona pellucida. Corona radiata. The population of follicular cells which suspend the oocyte in the vesicle. This population of follicular cells which suspend the oocyte within this antrum is what we are calling the cumulus euphorus. And finally, the population of follicular cells which are external to the antrum, these ones are the ones we call the granulosa cells. All right, I've told you that this is the part that is ovulated. So when this is ovulated, number 4, the cumulus euphorus will cease to exist, but the granulosa cells will definitely remain within the ovary while this one goes away. It's like when a girl is married, kuna wale wanabaki, yeah, man. Okay. Now look external to the granulosa cells. There are some cells of the ovarian stroma external to the granulosa cells. The cells of the ovarian stroma external to the granulosa cells are known as the thicker folliculi cells. You can just call it thicker folliculi, this region here, thicker folliculi. They are cells of the ovarian stroma that are external to the granulosa cells. Now look, we have said this is the mature follicle, this is the oocyte, or rather the structure that is ovulated, and so this is what happens during ovulation. The oocyte goes, the zona pellucida goes, and the corona radiata goes, and that is what you're seeing here. The oocyte, zona pellucida, and corona radiata, everything has gone. What remains in the ovary is this one, and that is what constitutes this one. We call the complex that remains in the ovary the corpus luteum. So what is corpus luteum? Corpus luteum represents the remnants of the follicle after ovulation. These remnants consist of the following cell types. Remember, the granulosa cells remained. The granulosa cells become what we call the granulosa lutein cells. Also remember, the thicker folliculi remained. The cells of the thicker folliculi constitute what we call the thicker lutein cells. The point here is these are the cells of the corpus luteum. To distinguish them from the cells of the Graafian follicle, we are adding that lutein. The purpose of the corpus luteum is to secrete hormones after ovulation. Before ovulation, the follicle is the one that secretes hormones. After ovulation, the corpus luteum secretes hormones. But the corpus luteum does not last forever. It only lasts 14 days from the time it is formed up to the time it disappears, 14 days. These 14 days represent the second half of the female reproductive cycle, where the ovulation is mid-cycle, and then before ovulation, it was the time that the follicles were maturing. Good. That is the process of oogenesis. I want to divide you into your small houses for 5 minutes, during which you are going to discuss the question projected. So please participate, talk about the differences between spermatogenesis and oogenesis. We've looked at almost all of them. Okay, so as we normally do, something will pop on your screen. Just accept, even if you don't like the people I will have given you. Okay, ready? Okay, let me put the timings well first. Okay, you should be ready now. I've given you 6 minutes. Halloween, you've called me to your group. Is there an issue? Joy? Faith?
Yes?
Is there an issue with your group?
No.
Okay. All right, I believe you're done with that exercise. Very important exercise. Now let's finish. I will now talk about clinical application of the science of gametogenesis. When you talk of clinical application, doesn't necessarily mean that we are going to utilize this clinically. It also means that we are trying to understand some of the abnormalities. So one is that you can have abnormal gametes. Gametes can be abnormal. For the oocytes, it could be that a single follicle has more than one oocyte. So those are abnormal. Rarely will such oocytes be fertilized for some reason. If they are, then rarely they may lead to twin gestation. Most of the time, they're not fertilized. Most of the time, they are infertile. You can also have abnormal sperms, the way you can have abnormal oocytes. For the sperms, you can have abnormal sperm morphology. Abnormal sperm morphology is termed as teratospermia. Teratospermia is when you have abnormal sperm morphology. You can have a sperm with the two heads, like this one, bure kabisa, or this one, two tails, or this one, small tail, or this one, kichwa kubwa tu, or this one, kichwa ndogo sana. All these are abnormal morphologies of sperm. The term given to sperm abnormal morphology is teratospermia. Apart from teratospermia, you can also have aneuploidy. We had talked about aneuploidy before in this class when you are talking about cell biology. Aneuploidy is when you have abnormal chromosomal number. Now this comes about if there is non-disjunction during the first meiotic division. Remember, during meiosis 1, homologous chromosomes are supposed to separate. For those who read on cell cycle and cell division, you understand that. During meiosis 1, homologous chromosomes are supposed to separate. If homologous chromosomes don't separate, then it means that the daughter cells, in this case, the secondary oocyte or the secondary spermatocyte, any of them may have an abnormal, okay, both of them will have abnormal number of chromosomes. One cell will have 22 chromosomes and another one will have 24 chromosomes. If that is translated also to the cells that finally will participate in fertilization, then it means that if one gamete has 22 chromosomes in total, and that gamete fuses with a normal gamete, the resultant zygote will have 45 chromosomes, and that is what we call monosomy. I gave you examples of monosomy syndromes, and a good example is Turner syndrome, 45x0. Similarly, if the gamete with an extra chromosome fuses with a normal gamete, then it means that the resultant zygote will have 47 chromosomes. And that is what we call trisomy syndrome. There were various examples of trisomy syndromes that we talked about. Trisomy 21, trisomy 18, trisomy 23, which we called Klinefelter syndrome, and perhaps also we talked about the triple X syndrome. Now I want to pose a question. Apart from aneuploidy, I want to pose this question to you. We agreed that the primordial germ cells migrate from the yolk sac and allantois, and they should invade the developing gonad. The question is, if they don't go there, and by saying that, I mean the gonad does not have the primordial germ cells, what would happen? So think about it. It means that the developing testis or developing ovary does not have a primordial germ cell, which means will not have the gamete stem cells, which means it will not have the sperm or the ovum at all. So it goes without saying that that person will be infertile. And it is not just infertility. Coupled with that is that this particular gonad will not develop normally. Now, I want to pose a question to you. We have said that such a gonad will not develop normally. That condition is called gonadal dysgenesis. That condition where the gonad does not develop normally. We call it gonadal dysgenesis. Now, this is the question to you. If a child, if a fetus has gonadal dysgenesis, let's say this fetus, the genotype was 46XY. The genotype is 46XY, but the gonad has not developed normally. The fetus has gonadal dysgenesis. Which anatomical gender will this child be? Will it be male or female? And I am more interested in the reason than in the answer. So if you say male, you need to give me a reason. If you say female, you need to give me a reason. Anyone wants to try? Just unmute your mic and say, I am usually a bit slow in checking the charts. I'm not as fast as you people. So you can unmute yourself and answer. Kwani mulienda?
Okay, Mwalimu, can I try?
Yes, Nathaniel, thank you.
Okay, according to what I think, okay, this is a male.
Okay.
And the reason is because yeah, the male androgens are present.
Okay. Okay, so good thinking, Nathaniel. Let me throw it back to you again. So where are the male androgens coming from in this particular child?
The testis.
Okay. So you've answered correctly that if the testis is there, then it will produce androgens, and androgens will cause virilization. Virilization is the patterning towards male pattern. However, what you missed is that the gonad is not present. We have said here that the testis is underdeveloped and not functional. So it's just fibrous connective tissue. Therefore, we don't have androgens in this child. So someone else to give me another reason. Any crash I measure? Anyone with another reason? Okay, this child will be female. As a matter of fact, all of them become female. I gave you a reason some time back. You people have forgotten. But let me repeat. In terms of sex determination, we said that there are 3 steps that are involved in sex determination. The first step is what we call genetic sex determination. Genetic sex determination occurs at fertilization. We just look at which type of sperm has entered the oocyte. Is it a Y sperm or is it an X sperm? If it's an X sperm, then it means that the zygote will be XX. And that means female because we don't have Y. If it's a Y sperm, then it means that the resultant zygote will be XY. And that means male because you have Y. That is genetic sex, or others called embryonic sex. It is determined at fertilization. The second step in sex determination is gonadal sex determination. It simply means, is there a testis or is it the ovary forming? What determines the formation of either is actually the availability of the Y chromosome. If the Y chromosome is present, then the gonad that will form is the testis. If the Y chromosome is absent, which means XX, then the gonad that will form is the ovary. The third, so that is the second sex, the gonadal sex. Testis means male and ovary means female. Gonadal sex determination occurs between the 6th and the 10th week of development. After that, we talk about the anatomical sex, or others call the phenotypic sex. The phenotypic sex simply answers the question, which type of reproductive organs do you have? Do you have a clitoris or is it a penis? Do you have a cleft down there or the things are fused together? If it's cleft, it's female. If it's fused, male. And the like. Do you have a prostate or you have a uterus? Do you have a vas deferens or is it a fallopian tube? So such like things. Now, what determines the kind of organs that form is actually the activity of androgens. If you have androgen activity, then the reproductive organs that form are the ones of the male pattern. If you don't have androgen activity, the reproductive organs that form are of the female phenotype. So in this child, we are saying that the genetic sex is XY, so male. The gonadal sex is indeterminate because we don't have a gonad. There's no testis, there's no ovary. It is indeterminate. If there is no gonad, then it means there'll be no androgens, at least not enough to cause virilization. Therefore, the maternal estrogens will override. There'll be no androgens, but the maternal estrogens will override. So the external genitalia of this child will be of female phenotype, irrespective of the genetic makeup. All of them are female. Whether they are XX or they are XY, they'll be all female. extragenitalia. I'm not talking about genotypic sex. I'm talking about the anatomical sex, the phenotypic sex. Okay, one last thing. Still debating around the fact that primordial germ cells have not migrated to the developing gonad. In the previous slide, we were looking at what happens to the developing gonad. We've said that it will be underdeveloped. Now let's think what happens to the primordial germ cells that have gotten lost. If primordial germ cells find themselves in a place where they shouldn't be, ideally they should find themselves in the testis or in the ovary, but they may not get there. So if they find themselves in an ectopic site, what happens to them? That's our question here. Now, this is what happens. Usually the cells will die, and you pray they do die. Because if they don't die, then they'll grow into a tumor. Such tumors are very interesting. Remember, primordial germ cells are pluripotent cells. What that means is that they have the capacity of forming multiple tissue lines: epithelial, connective, nervous, muscular. And even those connective tissue could be adipose tissue, could be fibrous tissue, could be bone, could be cartilage, anything. They have all that potential. Now think through. If these cells don't die, they'll grow into a tumor. Such tumors are called teratomas. Tumors which arise from pluripotent embryonic cells. They have the capacity of forming multiple tissue lines. We call them teratomas. Some of these tumors a child can be born with, like this one. Very ugly. These are teratomas. It doesn't matter where the primordial germ cells go. They can even find themselves in the brain, I'm telling you. They can find themselves in the mouth, like this one. They can find themselves in the thorax. Wherever the primordial germ cells find themselves in, they can become a tumor. We call those tumors teratomas. They could be in the sacral regions. These are still teratomas. These are examples of tumors that actually a child can be born with. They can be congenital. By the time the child is being born, there's already a tumor. They occur due to loss of primordial germ cells. The primordial germ cells got lost. All right. I believe now I'm done with the lecture. As I told you, we will not start on fertilization. We can do this next time. No hurry. So I'll invite you for questions.